In this lesson, we will talk about the Compton effect, a phenomenon that could only be explained if we think of photons as having momentum. The idea of light behaving like particles initially met a lot of resistance from scientists. It was about a couple of decades after Einstein explained the photoelectric effect that another phenomenon, known as the Compton effect, bolstered the notion that light behaves like particles when interacting with electrons. The Compton effect could be explained by assuming that photons have momentum, which is associated with particles but not waves. A schematic diagram of the experimental setup is shown here. X-rays with known wavelength are fired at a sample. The wavelengths of light scattered at various angles are then observed. Here, the detector is placed so that the waves of light scattered at a desired angle can be observed. In this illustration, theta is the angle between the original X-ray and the scattered light being observed. Here are the typical results of Compton's light scattering experiments. Here's the spectrum of light observed at theta equals 0. Theta equals 0 means the detector is on the opposite side of the sample as the original X-ray. The spectrum is a plot of intensity versus wavelength. It shows one peak, which occurs at the same wavelength as the original X-ray. At a 45-degree angle, two peaks are observed. One corresponds to the same wavelength as the original X-ray, and the second one is at a longer wavelength. A similar result is observed at 90 degrees. One peak is at the same wavelength as the original X-ray, but the second peak, the one at the longer wavelength, is further away. The classical electromagnetic wave theory of light predicts that the wavelength of the scattered light should be the same as the incident light. So how do we explain these observations? Here's the Compton's explanation for the observed shift. Light behaves like particles when they interact with electrons. Particles have momentum, and Compton derived how the momentum of a photon is related to its wavelength. From the photoelectric effect, the energy of a photon is equal to h nu, where h is Planck's constant and nu is the frequency of the light. It's also equal to hc over lambda, where lambda is the wavelength. We can see that a change in wavelength means a change in photon energy. Since longer wavelengths means lower photon energy, an observed shift to longer wavelengths suggests that photon has lower energy after colliding with an electron. From Einstein's special theory of relativity, the total energy of a particle is such that its square is equal to p squared times c squared plus m naught squared times c to the fourth power. Here, p is the momentum and m naught is the rest mass of the particle. The rest mass of a photon is 0. Therefore, m naught squared times c to the fourth power will be equal to 0 for a photon, and E will just be equal to P times C. Since E is also equal to hc over lambda, it should be easy to show that the momentum of a photon is equal to h over lambda. In other words, the observed shifts to longer wavelength implies a decrease in both energy and momentum of the photon due to its collision with an electron. Compton was then able to derive an expression that agreed well with the experimentally observed wavelength shifts by assuming conservation of linear momentum and conservation of the total relativistic energy when a photon collides with an electron. Assuming the electron is very loosely held in the atom and is initially stationary, Compton determined the shift at angle theta to be given by this equation. Delta lambda is equal to h over m naught times c times 1 minus cosine theta. Here, h is Planck's constant, c is the speed of light, and m naught is the rest mass of the electron. The quantity h over m naught times c is called the Compton wavelength of an electron and is equal to 2.43 picometers. A picometer is 10 to the negative 12 meters. Okay, we've explained what happened to scattered photons at the shifted wavelength. A photon at the shifted wavelength has lost energy and momentum due to its collision with an electron. But what about photons in the unshifted wavelength, which are also observed at all angles? Well, obviously, these photons have neither lost nor gained energy and momentum, but why haven't they? The explanation is that they collided with inner electrons, which are very tightly held. An inner, tightly held electron stays with the atom, and we can instead think of the photon as having collided with the entire atom. That means that in the expression that Compton derived for the wavelength shift, we plug in the rest mass of the entire atom for m naught instead of the rest mass of the electron. The lightest nucleus, which is one proton, is about 2,000 times more massive than an electron. So, how would plugging in a much larger value for m naught affect delta lambda? We would expect delta lambda to be much smaller, small enough that the shift is undetectable. Suppose a 0.100 nanometer photon hits a stationary electron in a head-on collision and recoils directly backward. Calculate the wavelength of the scattered photon. Then calculate the kinetic energy, momentum, and speed of the electron after the collision. We use the equation that Compton derived for the wavelength shift. The wavelength shift, delta lambda, is equal to h over m naught c times 1 minus cosine theta. Here, h is Planck's constant, m naught is the rest mass of the electron, and c is the speed of light. Theta is the angle between the direction of incident light and that of the scattered light. We can see that this angle is 180 degrees or pi radians. Plugging in the numbers, we get delta lambda equals 4.85 times 10 to the negative 12 meters. This is about 4.86 picometers as expected, since the Compton wavelength h over m naught c is 2.43 picometers for an electron and cosine of pi is negative 1. Note that 1 minus cosine pi is equal to 2, and 2 times 2.43 picometers is 4.86 picometers. The incident wavelength, lambda sub I, is given as 0.100 nanometers. Adding the wavelength shift to this gives us the final wavelength. The wavelength of the scattered light is 0.105 nanometers to 3 significant figures. Additional digits are shown here since we are going to use this number for further calculations. Once we know the initial and final wavelength of the photon, we can easily calculate the kinetic energy of the electron. The initial energy of the photon is hc over initial wavelength. The final energy is hc over the final wavelength. So the difference between them is equal to the kinetic energy of the electron. Plugging in the appropriate values for h, c, and wavelengths, we find the kinetic energy of the electron to be 9.19 times 10 to the negative 17 joules, or 574 electron volts. These should have only 3 significant digits, but more digits are shown since the values will be used for further calculation. From the kinetic energy of the electron, we can determine its momentum. Here's how. The kinetic energy is also equal to the difference between the total relativistic energy of the electron and its energy at rest, which is mc squared. Note that in the expression for the total relativistic energy, the momentum p is the only unknown. Remember that m sub e is the rest mass of the electron and c is the speed of light. Since we have already calculated the kinetic energy of the electron, we just need to rearrange this entire equation to solve for p. If we do this, then after plugging in the known values, we find that the momentum of the electron is 1.29 times 10 to the negative 23 kilogram meter per second. Here's an easier alternative way of finding the momentum, but this will only work if theta is 180 degrees. Conservation of momentum requires that the sum of the momenta of the electron and photon before the collision is equal to the sum after the collision. Before the collision, the momentum of the electron is 0. For the photon, the momentum is h over lambda sub I in the forward direction. After the collision, we're representing the momentum of the electron here as p sub ef. And the momentum of the recoiling photon is negative h over lambda sub f. Note that it is negative since it is moving in the opposite direction. Solving for P sub EF, we find that the momentum of the electron to be 1.29 times 10 to the negative 23 kilogram meter per second, which is the same answer we got earlier. Note that you cannot use this approach if theta is not 180 degrees, because you'll need to resolve the components of the momentum vectors. Finally, let's calculate the speed. Momentum is defined as mass times velocity. So if we know the momentum and mass, calculation of the speed v should be straightforward. In general, we need to write our mass m as the rest mass m naught divided by the square root of 1 minus v squared over c squared. The calculation for v is not as straightforward as simply dividing the momentum by the mass, since v also appears in the expression for mass. But it's still relatively simple to algebraically manipulate the equation to show that v is equal to p divided by the square root of m naught squared plus p squared over c squared. Plugging in the rest mass of the electron for m naught and the momentum that we calculated earlier gives us a speed of 1.42 times 10 to the 7 meters per second. What would happen if we use the non-relativistic formula if we simply divide p by the rest mass? Then we find that the speed is 1.42 times 10 to the 7 meters per second. Note that the two numbers agree to 3 significant digits. Recall that the speed of light is 3 times 10 to the 8 meters per second. So this speed is about 5% of the speed of light. It's when we're close to the speed of light that relativistic correction becomes important. If we're dealing with speeds less than 10% of the speed of light, ignoring relativistic correction should be okay if we don't need more than 3 significant digits. For this problem, our final answer should only have 3 significant digits, so it's okay. Let's now take a look at how to determine the final momentum of the electron for a more general case, where theta can be anywhere between 0 and 180 degrees. The procedure for calculating the wavelength shift and kinetic energy of the electron is the same as in the earlier example. So in this example, we will focus on calculating the momentum of the electron. Suppose a 0.100 nanometer photon hits a stationary electron and is scattered at a 45-degree angle from its original direction. Calculate the magnitude and direction of the electron's momentum after the collision. Let's take the direction of the incident photon as the x-axis. Here's the vector representing the initial momentum of the photon. Let's call this vector p sub I. Its magnitude is h over lambda sub I, where lambda sub I is the wavelength before collision. Here's the vector representing the momentum of the scattered photon. Let's call this final momentum vector p sub f. Its magnitude is h over lambda sub f, where lambda sub f is the wavelength of the scattered photon. The angle between the initial and final momentum vector is theta, which in this case is 45 degrees or pi over 4 radians. Here's the vector representing the momentum of the electron after it collides with the photon. Let's call this vector p sub e. Notice that we put the tail of vector p sub e to coincide with the head of the vector p sub f. Then draw the arrow for vector p sub e so that the head coincides with the head of vector p sub I. This is because conservation of momentum implies that the sum of the momentum vectors after collision must be equal to the sum of momentum vectors before collision. The sum of the vectors after collision, p sub f and p sub e, must be equal to 0 plus p sub I. Note that the momentum of the electron before the collision is 0. Let's move vector p sub e so that the tails of all the vectors are superimposed. We can specify the direction of vector p sub e by stating the angle that this green arrow makes with the x-axis. Let's call this angle alpha. The y components of the sum of vectors p sub f and p sub e should add up to 0. Since p sub I has a 0 component along the y-axis, Therefore, P sub f times sine of theta plus P sub e times sine of alpha equals 0. Similarly, the x components of vectors P sub f and P sub e should add up to the magnitude of vector P sub I. Since vector P sub I is parallel to the x-axis, therefore, P sub f times cosine of theta plus P sub e times cosine of alpha equals P sub I. Let's see how we can determine alpha. Let's rearrange the expression for the y components so that only the component for vector P sub e is on the left-hand side. We get P sub e times sine alpha is equal to negative P sub f times sine theta. Similarly, we rearrange the expression for the x components so that only the component for the electron momentum is on the left-hand side. We get P sub e times cosine alpha equals P sub I minus P sub f times cosine theta. Dividing this equation by this equation gives us this equation for tangent alpha. Remember that sine alpha divided by cosine alpha gives us a tangent alpha. Note that all quantities on the right-hand side of this equation are known. P sub f, the magnitude of the momentum of the scattered photon, is h over lambda sub f. P sub I, the magnitude of the momentum of the incident photon, is h over lambda sub I. And of course, theta is the angle between the photon momentum vectors. If we can calculate tangent alpha, we should be able to calculate alpha itself using the inverse tangent or arctangent function.
Finally, we can calculate the magnitude of the electron's final momentum as the square root of the sum of the squares of the components. Here's the y component, and here's the square of the y component, and here's the x component, and here's the square of the x component.
Here's a summary of the solution to this problem. Given theta is 45 degrees or pi over 4, we can calculate the Compton shift for the wavelength and find it to be 7.1 times 10 to the negative 13 meters. The incident wavelength is 0.100 nanometers. To this, we add the Compton shift to get the wavelength of the scattered photon. The photon momentum is h over lambda, so these are the magnitudes of the photon momenta. P sub I before the collision, and P sub f after the collision. Now we have enough information to calculate tangent alpha since we know P sub I, P sub f, and theta. Taking the inverse tangent of tangent alpha gives us an alpha of negative 67 degrees. Note that the negative sign just means that 67 degrees is measured clockwise from the positive x-axis.
Finally, we can calculate the magnitude of the electron's momentum. It's just the square root of the sum of the squares of the components.